Welcome to The Explainer. Today, we're diving into a new blueprint for solving some of our planet's biggest problems. It's a university course that's creating a new kind of environmental engineer, one armed with AI to tackle everything from water shortages to climate change. So let's take a look at what the future of engineering is really all about.
So here's our roadmap. First, we're going to explore why this huge shift is even happening right now. Then, we'll get into the nitty-gritty, the actual AI language these students are learning. After that, we'll see it in action, cleaning our water and building smarter cities. And we'll wrap up with the really big question. What is our responsibility when we wield this kind of power?
Okay, so what's the real driver here? Why is a course like this more than just a simple update? Why is it a fundamental rethink of what it even means to be an environmental engineer today?
Well, the bottom line is that our environmental problems are just moving too fast. We're dealing with challenges that are way more complex, and they're hitting us with a speed we've never seen before. The traditional engineering playbook, as brilliant as it is, was built for a much slower, more predictable world. It can't keep up anymore.
And this slide right here illustrates that shift perfectly. On one side, you've got the traditional models. They're built on this solid foundation of physics, super reliable, but often slow and kind of rigid. On the other side, you have data-centric AI. Now, instead of just relying on old formulas, it learns directly from these massive, messy streams of real-world data. And that lets it predict and adapt to things in real time.
Right, so how do you even start teaching this stuff? Well, the course kicks off with the absolute fundamentals. It's about giving students the basic vocabulary of AI before they can even think about building with it.
First up is what's called supervised learning. This is pretty much teaching by example. You feed the AI a huge data set where you already know all the right answers. Think thousands of water samples, each one labeled with its exact quality level. The AI just churns through that data until it learns the patterns and can predict the quality of a brand new sample.
Next, we have unsupervised learning. Now here, you do the opposite. You give the AI a completely messy, unlabeled pile of data, and you just ask it to find the structure all by itself. So for example, you could give it data on thousands of random pieces of trash, and it might figure out on its own that there are natural groups here, like plastics, organics, and metals, without ever being told those categories existed.
And finally, there's reinforcement learning. Honestly, the best way to think about this is like training a puppy. You create a digital agent that learns through pure trial and error. When it does something right, like releasing just the perfect amount of water from a dam to get the most power without causing floods, you give it a little digital treat, a reward. And over millions and millions of tries, it eventually learns the absolute best strategy.
So once they've got those core ideas down, students get a whole AI toolkit. They learn about all these specific algorithms for specific jobs. You want to teach an AI to recognize recyclable bottles in a picture? You're going to use a convolutional neural network or a CNN. You need to predict how a river's flow is going to change over the next week? That is a job for a long short-term memory network, or LSTM. It's all about picking the right tool for the task.
Okay, now this is where all that theory starts to get really, really interesting. The course takes this new AI language and immediately applies it to one of our most critical resources, water.
So just imagine a wastewater treatment plant for a second. The people running it need to know the quality of the water right now to make the right adjustments. But the traditional lab tests for some of the most important pollutants, they can take up to 5 days. And that is a huge delay where all sorts of things can go wrong.
So the solution they learned to build is what's called a soft sensor. These are basically AI models that take in all the easy-to-measure data like flow rate and pH to predict the really complicated lab results instantly. They act like virtual instruments, giving operators the real-time feedback they've always needed.
And the problem doesn't stop once the water is clean. Think about the journey to your tap. Our cities lose an absolutely staggering amount of perfectly good water from these tiny, hidden leaks in hundreds of miles of pipes buried underground. Finding them is a classic needle-in-a-haystack situation.
And the AI solution for this is just so elegant. It analyzes pressure and flow data from sensors all across the entire network. Over time, it learns the system's normal heartbeat. The very moment it detects a tiny flutter, a change that signals a leak, it can pinpoint the location for repair crews to go in and fix it.
Okay, so let's zoom out. The syllabus then shows how these exact same AI principles can scale up from just a single system, like water, to managing the whole complex, tangled web of an entire city.
I mean, a huge headache for any city is just waste. If we want to recycle more and send less to landfills, we have to get better at sorting through these mountains of trash. a job that's usually slow, expensive, and frankly, pretty dangerous for people.
This is where those CNNs we mentioned earlier make a comeback. The syllabus walks students through how to train an AI on thousands upon thousands of images of trash. The AI then learns to see, and it can direct robotic arms to sort everything at incredible speeds and with amazing accuracy, pulling out plastics, paper, and organic waste.
But it's about more than just managing waste. AI is becoming this essential tool for urban design. As we plan the cities of the future, every single decision, where we put a building, what kind of trees we plant, it all has a huge impact on things like extreme heat and local air quality.
So students in this course learn to use AI to create these incredibly detailed simulations of city microclimates. These models can show planners exactly where planting trees or installing green roofs will have the biggest cooling effect. It's essentially using AI as a crystal ball to design cities that are just more resilient and better to live in.
And this all leads us to the final and, maybe the most important part of the whole curriculum. It looks to the future, not just at the next cool piece of tech, but at the huge ethical duties that come right along with it.
One of the wildest concepts they cover is the digital twin. Think of it like a hyper-realistic flight simulator, but for an entire water treatment plant. It's a perfect virtual copy that updates in real time with data from the real plant. Engineers can use it to test out crazy new ideas or simulate disastrous scenarios, all without touching a single real-world valve.
But that, of course, leads to the fundamental question that the course makes every student wrestle with. As we hand over more and more control of our essential infrastructure, our water, our power grids, our waste systems, to these incredibly complex algorithms, how much trust is too much? And the syllabus gives a very clear, very direct answer. This quote is basically a core principle of the whole course. AI is an unbelievably powerful tool, but it is not a licensed professional. When it comes to public health and safety, the buck still stops with the human engineer, period.
Then, in this final, fascinating twist, the course turns the camera back around on AI itself. You see, training these massive, complex models takes a ton of energy. It needs huge amounts of water to cool the data centers, and all the specialized hardware contributes to a growing e-waste problem.
And so, this is where we end. This is the ultimate challenge that these future engineers are being asked to solve. It's this incredibly complex balancing act, harnessing AI's amazing potential for good while staying painfully aware of its own environmental cost. Finding that balance, well, that's what's going to define the next generation of environmental engineering.